Today we are going to see about Tomasulos algorithm, which is used in current processors like Intel's i7. But let's see a version where it is first developed without speculation. We'll see what is speculation and how Tomasulo algorithm works in this video. So first we'll understand why we went for the Tomasulo's algorithm. See, in conventional like previous processors, like in older architectures, we were expected to have a in order execution and in order output of that execution, that is in order outcome of an execution. But that would potentially increase our clock cycle. Say for example, let's consider this example. Say for example, this div has writing its result to register number F4, and we are going to read that F4 in add. Here going to read that F4 from the result of the division operation. We are going to perform an addition, and then there is another instruction, say multiplication, which is irrelevant of these registers used here. But in conventional processors, like before Tomasulo's algorithm was introduced, what we'll do is we'll first finish the div. Since this is a true data dependency, we cannot do anything about it, but there is no dependency for this instruction. So why can't we move this instruction? Like, we can execute it before these div and add, and can expect the same result, because we don't have any true dependencies here. So say for example, our div is taking 15 clock cycles and our add is taking some 10 clock cycles. Then on the 25th clock cycle only, I can execute the multiplication instruction. But what Tomasulo's approach says that you can just perform, like, do these operations sequentially, since they cannot be resolved, since they are true data dependent. We cannot resolve them. So what we are going to do is we just schedule them as it is, but move this multiplication instruction before this, like parallelly schedule this multiplication instruction along with this division, so that you can minimize the number of clock cycles. Say for example, in 0th clock cycle, div is scheduled, and at the same time multiplication will also be scheduled. And say our multiplication operation runs for has to say 12 clock cycles. Our multiplication operation will complete at 12, but at the same time our division will complete at 15, and our add will utilize that result from the 15th clock cycle from the division operation, 16th clock cycle, and it will run to its completion to 26. So this is how Tomasulo's approach is saying. So you can complete these 3 sets of instruction in 26 clock cycle, whereas here if you performed it sequentially without Tomasulo's approach, you would have run for 50 clock cycles, which is huge. So Tomasulo's approach is far better to perform, Tomasulo's approach is far better in improving the clock cycles. After all, the ultimate goal of every architecture design is to reduce the number of clock cycles. Even if it is 1 clock cycle, we want it to be reduced. That's how Tomasulo's approach is to perform a in order issue and out of order execution. This is the key point of Tomasulo's algorithm. The basic, all these architecture is based on this key point. So we will issue each and every instruction in order, but the completion may be out of order. Say, let's see in this example itself, multiplication is supposed to be completing after our add, but since we ran it before these 2 instructions itself, we came to a result out of order execution result. We came to an out of order completion. So the execution as in completion here. So we came to an out of order completion. So we can potentially reduce the number of clock cycles because of such stalls. So how a Tomasulo algorithm is going to work is, and main thing we have to be notes that make sure we are having enough number of units also to perform these operations simultaneously. Say for example, if I had only one floating point multiplier and I cannot schedule both and div and multiplication to the same floating point multiplier. I have to have another unit, say for example FP2, to schedule this for div and schedule this for multiplication, or it can have a single floating point multiplier that have a pipelining in them. Say for example, our floating point multiplier has 20 stage pipeline, 20 stage. Our division will be start scheduled at 0th clock cycle, and multiplication will start scheduling. It will get scheduled at 3rd clock cycle. So what it will put is our in 20 stages, our division will occupy this slot, and then it will move to this slot. Meanwhile, the multiplication operation can move to this slot. So pipelining of the instruction is also, like pipelining of the unit is also possible in running for parallel execution. But a basic approach is to have enough number of multipliers available on the chip, and this is a design issue. So you're just going to see a generalized view of how a Tomasulos algorithm works. It is up to a particular manufacturer to have n number of multipliers and m number of adders embedded on a chip. So, and the second thing here is we are going to perform a out of order execution here. So since you are going to perform an out of order execution, there may be a chance like this F4 might get overwritten by another say for example here some add is here, it is writing to the same register, but this add could complete add could complete fast. So let's make it as another division operation that could run to its completion at this stage, and it wrote its value. Say for example, this is div 1 and this is div 2, f and a register is f4. This div 1, say for example our div 2 started later and div 1 started before. Now there may be a potential, say for example some kind of stall or something happened, and this div took say for example it completed at 20th clock cycle, but this ran into completion before 20th clock cycle, say for example in the 19th clock cycle. So eventually the result of div 1 only will be present in F4, but we need the result of div 2 to be present here. So in such scenarios also we have to handle. So for that purpose only, Tomasulo also introduced another set of buffers, that is called as reservation stations. This could hold these values. This could prevent this true data dependence for these kind of data dependence. Say for example, our data dependence, this type of data dependence is called as a write after write, that is our output dependence, because the output of both operations is returned to a same register. So such kind of dependence also has to be handled by this Tomasulos, and Tomasulo provides a facility for those for those type of dependencies also. So Tomasulos provides read after write dependencies, eliminates read after write, write after read, and write after write. It eliminates all these dependencies using providing an extra space for the registers to store, so that we can ultimately store the previous value or the required value in this reservation stations, and then we can perform the execution later. So but we need to know what is the content of the reservation stations to understand this whole algorithm clearly. So we call these data structures as bookkeeping operations. So it's just because it's like a temporary register. It's going to keep its value till the operation is going to be executed. So we call them as a bookkeeping operations. The first one is the reservation station. The reservation station contains this is the format of the reservation station. The first one is the name of the reservation station, where it will contain obviously like, say for example, this is a reservation station of an adder. We have 3 reservation station. It could have had so it could have had add 1, add 2, add 3. It's just a unique name for the reservation station slot. And and next is status, whether it is busy or free. And the next field is the QJ and QK field. So the QJ and the QK field is like, it's saying whether before going to QK we'll see what is VJ and VK, then we can understand QJ and QK. So let's take the previous example itself, div D F4, F2, sum F0, and add D F6, F4, F3. So let's consider this. For this added instruction, we have to fill this reservation slot. So here VJ and VK are the source operands here, and this is also the source operand here, but the functionality is quite different for QJ and QK. So VJ and VK is nothing but like, it's seeing what are the source operands. See, this is J and this is K. They have named it J and K, so we will just like, it's just naming convention. You can put A, VE, VA, VB or something, VJ and VK. And this in the VJ field we have the F4, that is the content of F4 has to be stored here, but this F4 is dependent on the previous instruction. It's not the value directly obtained from the register, it's dependent on the previous instruction. So this F4 is not readily available, but this F3 is readily available for us. So this F3 is put here, the content of F3 is put here, but for F4 it will make an entry. F4 is expected from which reservation station. Say for example, this is scheduled in a div 1 reservation station. It will put div 1 in the QJ field, expecting the result to be obtained from the reservation station named as div 1. So so QJ and QK puts the value if it is not readily available, whereas VJ and VK has the value if it is readily available. So an instruction can immediately be executed if both the QJ and QK fields are empty, or you can say it as VJ and VK fields both are available, then you can immediately schedule the instruction for execution. And the address field is for the load and stores operation for calculating the effective address. And this is the data that has to be stored for the load and store, and the operation name itself, whether it is an add, because adder can perform a subtraction operation also. So whether it is an add operation or a subtraction operation for an adder, and multipliers will have the whether it is a multiplication operation or a division operation. The operation, what is the operation? It is put out in this slot. And similarly in the registers also, they will apart from the data that has to be stored, they will have another field called as an RS tag. That is, if the register is supposed to be expecting a value from the outcome of this reservation station, that value will, like, that tag will be put here. Say for example, this addition operation tries to write it in F6. So F6 will be returned F6 value will be obtained from the add 1 reservation. Say for example, this is add 1. It will be obtained from add 1 reservation station. That tag will be put out here, so that when the result is broadcast onto this common data bus, this registers file will get its value from there, and it will just update the value into the register file, and it so that it can be available for the subsequent operations also. So that is the whole like operations, like whole bookkeeping operations that is required. And we'll emulate a small program also with the Tomasulos approach so that we can understand it clearly. And before that, we will see other components of the Tomasulos. And since we have in the reservation stations here, similar to a reservation stations, we call it as a load and store buffers. See here, since our reservation station, they don't need a queue, our reservation stations doesn't need a QJ and QK field for a store and load buffers, because either store you will have only one store operand, one source operand, and load we have one destination operand. So that is enough, right? So for that purpose, like this is modified to accommodate those particular operations. We have store and load buffers. We'll have the effective address and the data to be stored here. And apart from that, the entire architecture of a conventional CPU will be same. Now let's see how to emulate a program in this, and we'll understand how it is working. So let's see question. Now in this question we are given that we have to emulate Tomasulos approach. Let's assume it is without speculation. So we are going to perform a dual issue. So and the main thing I have forgot to inform us, in the Tomasulos approach, we usually without Tomasulos, what we will have usually we'll have a fetch, decode, execute, your memory write or something, and then you will have a write. And basically we'll combine these operations or to this one. We will combine the memory and the execution. So basically we have the four stages of a pipeline. So similar to that, in Tomasulos we will modify them as issue, execute, and write back. So where is the fetch is? Fetch is a separate complex unit. We assume that all the instructions are fetched and put into our cache. Okay, so fetch is a separate big operation. We will assume or is a perfect scenario for the fetch. Like there can be a cache miss, or you have to load it from the main memory, or main memory. If main memory itself doesn't contain, you have to load it from the second disk. So there is lot of operation to be performed. So we are going to assume it's a perfect scenario and everything is available in the cache, and it has been present, and we can pull it everything and put it into our instruction queue. So all the instructions are available in the instruction queue. So first fetches, we assume the perfect scenario, everything is available. So fetch is done previously and we are not going to bother about it. And issue is the only thing we are going to issue. The execute and the write back stage is the main thing we are going to get bothered. Actually, in the decode stage, we'll do two operations. That is, we'll issue the instruction into the decoding unit and read the operands. Read the operands value. And what we are going to do is, here we are going to do this read operand separately and pull this issue stage alone to a previous stage. Like we'll make the issue itself as a separate stage, and we'll assume if the operands are available, they readily will be put into our reservation station without any issue. And if it is not available, we'll just put a flag, say, hey, I need this operand, so you have to give me this operand. Like that, we'll put a flag and we'll perform the execution and the write back stage. So in Tomasulos approach without a speculation, we'll have three stages while emulating: issue stage, the executive stage, and the write back stage. But conventionally, it will have the fetch stage to be preceded by the issue. Now let's see this question. in this question we are seeing like given they have a separate functional units for say for they have given everything has a separate functional unit, so we don't need to wait for like structural hazards at all. So and they have given latencies for the questions. So the latency they have given us, add takes 3 clock cycles, multiplication takes 5 clock cycles, and we should, and like for the load and store they have not given, but we have to know like what a load will contain is a load will first perform the effective address calculation, then it has to go to the memory, here say for example cache, memory or cache, and it has to get the value from that. So execution stage of a load is 2 operations. You have to perform 2 operations. It has to be done in a separate clock cycles. Say for example this one is I, then we'll require I plus 1. So execution of a load will take 2 clock cycles, and the store similarly, the execution of a store will take 1 clock cycle for the effective address calculation and 1 clock cycle to write it to the memory. Okay, and this will, so store will also take a 2 clock cycle operation for execution. Now with this information we will go to solving this problem. So they have also given to emulate this code for a 2 iteration loop. So for 2 iteration, and they are given as a dual issue. So at a time our processor can issue 2 instructions. So for that we will emulate the Tomasulos algorithm without speculation. So if you will first okay, so the first I have already filled the instructions for 2 iterations. Here if you see like the same instructions from LD to BEQZ first time, and the second time we have given from LD to BEQZ. So for on the first operation we'll issue the load instruction. Since it's a dual issue, we'll issue both load and the multiplication instruction at the same clock cycle. The load and the multiplication operation at the same clock cycle, and already I said like load will perform a effective address calculation and then a memory operation, so it will take 2 clock cycles, so it will perform 2 and 3. Now after performing after fetching it from the memory, we will put it to our load buffers. If you see in the architecture, it will put it in the address memory unit, will put it in the load buffers, and we're going to write it to our CDB. And then we'll write it to our CDB, and then you'll write it to our floating point registers here. But any register, the register file it will write. So first we have to fetch it from the memory and then put it into our CDB, and then CDB will write it to the respective register. So here write back will have a write back stage for load. So in 4th clock cycle only the load will complete. So next operation, multiplication operation, F4, F2, F0. F2 is dependent on the load, and F0 is already loaded and somewhere. So it's here assumed as fixed. So F0 is fixed, F2 is to be loaded from the memory. So F2 is true data dependent on load. So we have to wait for the load to complete, but so we have to wait for this load to complete. This load completes at clock cycle 4, so we can start the multiplication operation execution at clock cycle 5. Now if we start it at clock cycle 5, add a multiplication takes 5 clock cycles, so it will 5, 6, 7, 8, 9. So 9th clock cycle it will complete its execution, and it will write it to the register number F4 at 10th clock cycle. Now again we have an LD, and then we have two issues. In the 2nd clock cycle we will have performed these 2 instructions issued to the functional units. So this issued at clock cycle number 2 can start its execution at clock cycle number 3, calculate its effective address, and perform the memory operation at clock cycle number 4. But if at all we are not following a Tomasulo approach, this issue, even though we have issued it, we should have waited for this load to complete, and we couldn't perform this operation before. We would have waited for all the subsequent operations to complete. So for that now we have the reservation stations to hold the values temporarily. So now we will perform the out of order execution also with this Tomasulo's approach. Hence we will have the 3, 4 here. Execution can start at 3, 4, and you will complete that operation and write back at 5. And multiplication operation is dependent on this previous load, and F8 is fixed. So if F6, multiplication can start at 6th clock cycle, and it will has 5 clocks of operation. So it will complete at 10, and it will write back to the register at 11th clock cycle. Now add and store will be issued at simultaneously, and add can start, and now add has F10, which is from the multiplication operation, and F4, which is from another multiplication operation. This is, say for example, this is M1, this is M2. It has to wait for both the multiplication to complete for the add to run. So if you see here, this multiplication completes at 10, so we can have F4 at 11, and this multiplication completes at 11, and we can have F10 at 12. So we can start this add only at 13, and it takes 3 clock cycles, so we will have 15 here. So, and it will complete at 16. Now since store is dependent on add again here, we have to wait for this write back to complete, and store so that store could store its value to the main memory. But so do we have to stall it here for 17? Because I had already said, like, first we have to perform a effective address calculation, then only we have to write it to memory. This effective address calculation is irrelevant of the previous outcome, so we can calculate the effective address immediately, but we have to wait for this add to complete to store it to the memory. So we will store it to the memory. But we don't have any write back because there is no register writing, or we don't put it to, like, we won't put the value into the CDB, so there is no write back operations here. Now again, on the next 4 clock cycle, two operations will be issued here, both the DAD-IO operations. Now both the DAD-IO are the integer operations. Here integer operations, let's assume it takes only 1 clock cycles, so it will both execute at clock cycle 5, and it will complete at clock cycle 6, and this is also completes at clock cycle 6. So that is a problem. Now in our architecture, if you see here, in the architecture, we had only one CDB, so at a time only one value we can write it on the bus. But this is again a design issue. Now if at all there is a multiple CDB available, we could have written multiple values into CDB. Say for example, CDB 1, this will be written into CDB 1, and this will be written into CDB 2. So multiple writes can happen at the same clock cycle. So this is again a design issue, so we will assume that multiple CDBs are available. Okay, so both these data you can write back at clock cycle 6. Now, and again we will assume mostly all the processors will have a single issue branch. You can perform a clubbed issue, say here also 5 and here also 5, but most of the processor performs a single issue branch, so that it could be easier for the rollback operation. We'll see a problem with Tomasulos, and in the problem, our life would have been simple if it was a single issue branch. So we'll make it as a single issue now, as of now. So this compare is, our processor will see that this is a branch instruction, so we'll make the compare instruction as a single issue. The compare depends on R1. R1 is available at clock cycle 7, so it takes only one clock cycle since it's an integer operation, one clock cycle, and it will commit to it will write it to CDB at clock cycle number 8. Branch will be issued at clock cycle number 6. It requires R3, which is available only at clock cycle 9, and there is no write back for branch because branch is just executing and just deciding whether to fetch the next instruction or not. So since we are asked to emulate for second iteration, we are going to perform the same iteration here, but this time there will be a bit change here. See, now branch is single issued, and we in the 9th clock cycle we know that we have to perform another iteration. So branch would have fetched, branch could have said like, there is hey, this is not completion, we have to do it. So before that itself we might issue the same instruction. If we have issued the LD and multi, or in some kind of branch prediction techniques, we might have issued our load and multiplication. But since there is no speculation facility available for this algorithm, this architecture, we have to stall this load till the outcome of the branch is known. So instead of proceeding at clock cycle number 8 itself, what you will do is we'll stall this load operation till the outcome of branch. Outcome of branch is known at 9, hence our load can execute only at clock cycle number 10, and then it will perform as memory fetch at 11 and write back at 12. So this is a problem here. Now we have to waste our functional units will be sitting our load buffers here. Load functional unit is load buffer, load store unit. The load store will be sitting idle for 2 clock cycles here. So that is a problem here, which we will resolve using our speculation. We'll see how a speculative processor can overcome this problem. Now in the since we have to wait for branch to complete, we are completed at 12. Now this multiplication operation has to wait for F2, hence it can start its execution only at 13, which takes 5 clock cycles for multiplication, which means it will take 17 clock cycle to complete, and 18 it will commit. This load can be issued at 8 and multiplication issued at 8, and our branch solved at 9, so hence we cannot start this at 9, we'll start it only at 10, and it will commit at 12. Say for example here also we assume that multiple CDB is available, hence this is not going to be an issue for us right now. Now if at all there is a single CDB also, we will see how to change that one. So if it will come right back at 12, and it will start its execution at 13, and it will perform till 17, and it will be available at 18 clock cycle, and F10 F4 both are available at 18, hence we will issue both this add and store. This can start at 19, which will perform till 21, commits at write back at 22, and this store can perform its FT or this calculation at 10 immediately. Why? Because our branch is resolved at 9 itself, hence we can perform immediately. If at all the branch is resolved at 10th clock cycle, we have to put 11 here. We have to make sure that after the branch is resolved only, all these second iteration operations, like all these operations takes after only the resolution of the branch. Execution has to be continued only after branch resolution. Now it will complete its effective address at 10, and but add has it has to wait for the result from the add, so it can perform the write at 2023, and there is no write back for store. And data use issued at 10th clock cycle, which can run in parallelly 12th clock cycle, and compare is again and you can see that branch is again a branch instruction, and we have to issue this as a single issue. So we'll have 11th clock cycle issued. Compare instruction will be issued at 11th clock cycle, and since it's dependent on, I think this is R3 and this is R1. Okay, so this is R1. So in R1 is available only at 12th clock cycle, so we can perform compare at 13, and it commits at write backs at 14, and branch can start its a branch will get its execution started at 14, 15, and it will complete its execution. It will start execution and complete by 16. So at the 16th clock cycle only we will know whether to stop the loop or perform the another fetch of the operation. So this is the the emulation of a without speculative Tomasulo algorithm. Now now let's say there is only one CDB is available. In that time, say for example, the first time we are encountered is multiple CDBs here. So what we have to do is, here we have to stall it for another cycle, so that it could be because since it is a structural hazard here, we don't have enough number of resources to perform this operation. So we stall it for a cycle and then perform the write. So even though this is stalled, we don't have it doesn't affect our compare here, because compare depends only on R1. So we don't have a problem. Now if you see here, let's see this 12 we have a problem. Now if you see here, this 12 has to be stalled for a cycle. Now if this 12 is stalled for a cycle, now F6 could have only received its value at 14th clock cycle, and it would have complete only at 18th clock cycle. You would have returned back into the register at only 19th clock cycle. Hence this add could perform only at 20th clock cycle and completed at 22nd clock cycle and committed at 23rd clock cycle. Since its add is available, add result is available at 23rd, we have to move it to 24th. So having one CDB, we have to resolve all these issues. Now until this it's fine. Now again, if you see that here we have another two data operations trying to write the CDB. Now we have to make sure these are also don't collide with the 12. So we try to write it at 13, but 13 we already have a load to be carried out here before, so we cannot write it at 13. 14 we can do, so we will write it at 14. So you'll see, so again this 12 we can write it at only 15, because 15 we don't have anything, and if we see here 14 we don't have enough CDB to write it, so we have to change it to 15. 15 is already occupied for this data U, so we have to move it to 16, which is not available. I think it's here, so we have to move it to 17th clock cycle for this write back to complete. But since this write back completes at 17, now okay, we have forgot this one also. So compare requires R1 to be available at 13, but it's complete at 12, but it completes at 14 only, so we can have it only at 15. It tries to finish at 16, but 16 is already occupied, so 17 comes 17 here, it's coming 17, so there is no problem. And RT is available only after 17, so this has to be changed to 18 clock cycle. So with only one CDB we had 24 clock cycles, and we have, if we had multiple CDB, one CDB, and if we had multiple CDB we would have completed by 23 clock cycle. So this having multiple CDB doesn't affect us much in this example, but in some cases it could give a faster performance. So usually a processor will have either one or two CDBs to avoid all these problems, so that the clock cycle can be reduced, and mostly the processor uses two CDBs. and we okay, now what happens if we now we see the perfect scenario where the load is to be continued for the like branch outcome is also success and we started. But say for example our load is here, if you see here, branch is saying like don't perform any branch, so we might have had the instruction queued up till 18th clock cycle. So 18th clock cycle, what we have till 18th clock cycle, instruction must have been loaded into our instruction queue. Say for example here, if you perform for another iteration, say third iteration, okay, let me pick a good color. So okay, this is performing for a third iteration, so 12 here, 13th clock cycle, these could have loaded into our instruction queue, and 14th clock cycle, this could have been issued for the 14th clock cycle, and this third instructions, third iteration we are performing. Okay, so in 13th clock cycle and 14, 15 this would have been issued, 16 this 2 would have been issued, and 17 this 2 is would have been issued, and in 18th this would have been issued. One complete iteration would have been issued before the execution of this branch is over. So this is again we have a problem of flushing the instruction queue. So without speculation, we now have to flush this entire instruction queue and have to fetch the particular instruction. All these problems are there. See for example here we are assumed there is no third iteration. If at all there was a third iteration, now this fetch would have been a smarter way. But if it has not happened, then all these fetch and all these issued is waste of resources, like waste of issuing all these things in the subsequent iteration, subsequent clock cycles. Instead of that, we could have taken an instruction from a fall through path. Say for example, this is some instruction here, some X. We could have directly fetched at 13th clock cycle, we could have fetched this instruction and we could have moved on, and we could have done that. But we don't know whether when this branch will fail and when this branch could succeed and go to this load. So that solely depends on our branch prediction. Our branch is taking load is taking from this 13th clock cycle, and if it has to stall till 18th clock cycle for it to complete execution. But we could have executed at 14th clock cycle itself, and we could have done this operation without knowing the outcome of the branch. This is known as speculation. That is, we are assuming that this load is to be executed and we are pre-calculating all these stuffs. But again we'll have an issue. Since we are pre-calculating, we cannot store it because we don't know whether the branch is successful or not. So we have to have some kind of extra hardware or extra logic to revert back the state if the branch condition fails. That is done with the help of a Tomasulo speculative execution, which we will see in the next video.